Should I share my screen?
Yeah, you could try it.
Okay. Not sure. Sorry.
Okay, go, Krishna.
Okay, yeah. So it's a great pleasure to welcome Bishal Deb from the University College London to give a talk in our seminar. He's in his closing stages of his PhD with Alan Sokal, and we look forward to this talk, the quadratic family of continued fractions and combinatorial features. Bishal.
So I would like to thank Gaurav and Krishnan and the other organizers for inviting me to give a talk at this seminar series. So today, so what I'll be talking here is joint work with Alan Sokal, my supervisor, and so some of it is ongoing, some of it is on the archive. So let me begin. Also, I mean, I may deviate somewhat from the abstract that I've sent. I think I've been quite ambitious with time, but let's see. I mean, depending on what time permits, I'll go accordingly. All right. So here is roughly the structure of my talk, and let me begin. So Still-just type continued fraction is a continued fraction of the following form. It looks like this. By the way, I hope my cursor is visible. Can somebody confirm?
Yes.
Okay, thank you. Okay. So a still-just type continued fraction is a continued fraction that looks like this. And outside of combinatorial literature, it's also called a regular C fraction or a regular continued fraction. But we will call it an S fraction or a still-just type continued fraction in this talk. So if we have a sequence AN, then we want to obtain a continued fraction expansion. So we take the ordinary generating function, and then we want to write it as a continued fraction if possible, where the alphas should be nice, suitably nice coefficients. By the way, when I put this expression, I mean as a formal power series. I do not, in this talk, I do not care about convergence issues. So I mean this totally both sides as formal power series, this identity should hold. And we want to classify these sequences by the growth rate of the coefficients alpha. So that is, when I say quadratic family, that is what I mean. So the where these still-just type continued fraction coefficients grow. So we want to look at the growth rates. So let's look at some, before going into the quadratic family, let me talk about the linear family a little bit. So, and give some examples. So when you have constant alphas, so when alphas are 1, 1, 1, 1, 1, and so on, these are the Catalan numbers. And when you have 1, 1, 2, 2, 3, 3, and so on, then the sequence AN is n factorial. And for Bell numbers, which count the number of set partitions, the alphas are 1, 1, 1, 2, 1, 3, 1, 4, and so on. And for 2n minus 1 double factorial, so this is simply the product of the first 10 odd numbers. The alphas are 1, 2, 3, 4, 5, and so on. So in these sequences, you can notice that, okay, so in the first one, the alphas are constant, and all the others have alphas growing linearly. So I'll spend quite some time, even though the title of my talk is quadratic family, I'll talk quite a bit about the linear family as well, especially the case of permutations. And let me first give some examples of sequences which have quadratic growth. So there are the tangent numbers and secant numbers, Genoki and median Genoki numbers, and even Springer numbers. So in this talk, I'll talk about the tangent and secant numbers, Genoki and median Genoki numbers. not about the Springer numbers, and I'll define what they are in some time. So let me now simply define these numbers. So tangent, secant, Genoki median. So let me begin with tangent and secant. So consider the uh, trigonometric functions secant and tangent, and take secant of t plus tangent of t, and look at this Maclaurin series expansion. And I call these coefficients E sub n. So if you take the even terms in this sequence, these are known as the secant numbers. And so the even terms are entirely contributed by the trigonometric function secant, and the odd terms are entirely contributed by the tangent function. And these are known as the tangent numbers. So the secant numbers have, so these are integers, these are positive integers. They have been studied combinatorially since 1889, I think, when Andre published interpretations for secant and tangent numbers. So which sort of started modern day algebraic and enumerative combinatorics. So the secant numbers and tangent numbers have these alphas. So it's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. Tangent numbers are 1 times 2, 2 times 3, 3 times 4, 4 times 5, 5 times 6, and so on. So now that I've defined the secant and tangent numbers, let me move on. Oh yeah, and Stilges had continued fractions for, so these continued fractions I think were discovered by Stilges. Somebody in the audience probably might know better than me and should correct me if I'm wrong. And classically, they were expressed using Borel summation or Laplace transform, those kind of things. In this talk, we are not going to go into that aspect. So I have a question for the audience, and somebody might know this better than me. I was asking Gaurav just before starting my talk. So I wonder if Ramanujan had rediscovered these continued fractions. Somebody can, I know that Ramanujan had rediscovered some continued fractions for elliptic functions, and so maybe somebody in the audience can tell me more about the history. So now let me define Genoki numbers. So we take this function, so take the tangent function, tan of t over 2, and then multiply it with tan, and do the series expansion. And these coefficients g sub n are Genoki numbers. And so the conventions vary in different papers. In our work, we follow this convention. We want the sequence to start at 0, and we want the numbers to be positive. So it's 1, 1, 3, 17, 155, 20, 73, and so on. So from this formula, you can see, you can write the Genoki numbers and relate them to the tangent numbers. So this is the formula. So the Genoki numbers are also related to the Bernoulli numbers through this formula. So in our notation, this is the formula. I've checked this on Mathematica just before this talk to be sure. So the alphas for Genoki numbers are 1 times 1, 1 times 2, 2 times 2, 2 times 3, 3 times 3, 3 times 4, and so on. And I think this was first discovered by, this was first proved by Vienno in 81. And also there is another sequence called the median Genoki numbers. So this is one way of describing the median Genoki numbers. And the first few numbers are 1, 1, 2, 8, 56, 608, 9, 24, 40. By the way, I don't expect you to remember the definitions of Genoki and median Genoki numbers. We'll go into something more tractable in a while. So for the median Genoki numbers, however, there is no nice closed form known for the exponential generating function, at least to our knowledge. And the alphas here are 1 squared, 1 squared, 2 squared, 2 squared, 3 squared, 3 squared, and so on. So this was again proved by Vienno. So let me now give you a description of Genoki and median Genoki numbers, which you can remember throughout this talk. So the Genoki numbers are the cardinality of this following set. So these are permutations on, so these count permutations on 2n letters such that whenever you have an even index 2i that's bigger than sigma of 2i, and whenever you have uh, an odd index 2i minus 1 that's less or equal to 2i sigma of 2i minus 1. This is true for every 2i and every 2i minus 1. And now the median Genoki numbers. So you have a strict inequality here and a weak inequality here. If you replace that with both strict inequalities, then these numbers are counted by median Genoki numbers, H sub n. Also, an interesting fact is, if you instead have weak inequalities in both, so if you have one strict, one weak, that's Genoki, both strict, that's median Genoki. And if you have both weak inequalities, then this will be shifted median Genoki. So these are also counted by median Genoki numbers, but now the sequence is shifted. So this is H sub n plus 1. So surprisingly, this combinatorial interpretation for the shifted median Genoki was only discovered like very recently, 2019. So these are known as D permutations or Dumont-like permutations. So this was discovered by Alex Lazar and Michel Vaux. And we call these as D derangements. So derangements refers to permutations without fixed points. So since you have strict inequalities in both, so we call these D derangements, and we call these as DE semi-derangement. So we use the word semi-derangement. So we to mean that you do not have even fixed points, but you can allow odd fixed points. And this is how you can remember Genoki and median Genoki numbers. So let's look at an example. So this is an example of a D permutation. So these are all the i's. So we have taken a permutation on 8, where n is equal to 4. So on 8 letters. So 1 goes to 7, 2 goes to 1, 3 goes to 3, and so on. And you can see that for every even, you're going to something lower. So 2 is going to 1, 4 is going to 4. That is fine. 6 is going to 2, and 8 is going to 5. And for the odd ones, you're going to the image is something larger. So 1 goes to 7, 3 goes to 3, 5 goes to 6, and 7 goes to 8. So these are D permutations. So the even indexes, they go to values which are less or equal to them. And the odd indexes go to values which are larger or equal to them. And let me also give a non-example. So this permutation, so this is the permutation where 1 goes to 2, 2 goes to 3. So here the even goes to something larger and the odd goes to something smaller. So this is not allowed. So this is not a D permutation. And let me just go back and say that D permutations with no fixed points are D derangements. And if you allow fixed points of one parity, we call it DE semi-derangement or DO semi-derangement, depending on the ones that you don't allow. So I have described some of the sequences and the combinatorial interpretation for the Genoki and median Genoki. Is there any question at this point? Anything from the anyone has any questions? Maybe I'll wait for a few seconds. Okay. Oh, by the way, feel free to interrupt at any point. So now, before going into the story of D permutations, I would like to talk a bit about the story of permutations and the linear story. So continued fractions for permutations have been found and studied by various people over the years. So earlier I described what's a Stilges type continued fraction. Now I'm going to talk about something called a Jacobi type continued fraction, or it's also known as an associated C fraction outside of combinatorial literature. So if you take the ordinary generating function for factorials, so 1 plus 1 factorial times t and so on, then this has a Jacobi type continued fraction, which looks like this. So it's 1 minus, so you have the odd numbers here and the squares of numbers, which are coefficients of t square. So now from this continued fraction, so you can obtain this continued fraction just by using this formal power series and uh, so the Still-Just type continued fraction, oh, I forgot to mention, that was first discovered by Euler in 1746 and published in 1760. And there is a contraction formula which converts a Still-Just type continued fraction to a Jacobi type continued fraction. So all of this can be done from using formal power series. However, this is not giving any extra information on permutations. And the thing is, we can obtain a lot of combinatorial interpretation from continued fractions and count permutation statistics. So let me give some. So before going into that, uh, let me define this thing which Sokal and Zeng call cycle classification. So for every permutation sigma, we consider an index I and then compare it with sigma of I and sigma inverse of I. And here are these 5 possibilities. So if I is less than both sigma inverse of I and sigma of I, we call it a cycle valley. If I is bigger than both sigma inverse of I and sigma of I, these are known as cycle peaks. I is bigger than sigma inverse of I and less than sigma inverse of sigma of I. That's called a cycle double rise. And similarly, similarly, you also have a cycle double fall. And the fixed point is when I is equal to sigma of I, and hence has to be equal to sigma inverse of I. So, so every index is one of these 5 possible types. And now we can consider this 5 variable polynomial. So fix an n, and then consider this polynomial in variables x1, x2, y1, y2, and w, and take where you give this weight to every permutation. So x1 counts the number of cycle peaks, x2 counts the number of cycle double falls, y1 counts the number of cycle valleys, y2 counts the number of cycle double rises, z counts the number of fixed points. And you compute this. Your computer should be able to compute the first 10 or 12 in a reasonable amount of time, maybe the first 10 in a reasonable amount of time. And if you try to compute the J fraction, you will find that under the cycle classification, you have the following J fraction for these polynomials. By the way, so if you substitute 1, 1, 1, 1, 1 in this polynomial, you'll just get n factorial over here. And this J fraction would be the J fraction for that we had in the previous slide. So now you can see that the coefficients of t square are contributed entirely by cycle peaks and cycle valleys. So these are x1, y1, 4 times x1, y1, 9 times x1, y1, and so on. And the coefficients of t over here, these are contributed by fixed points, cycle double rises, and cycle double falls. And you can say, okay, this is good. We've made some progress. Let's try and prove it. I'm not going to go into the proofs for these. This is good progress, but then I guess maybe we are a bit more greedy, and we want to understand that there is this these 4 x1 y1 and then 9 x1 y1, and really we want to understand what's the contribution of cycle valleys and what's the contribution of cycle peaks here, and similarly also for cycle double rises and double falls. And so to obtain more stratified information, what we can do is we can do something called the record classification. So previously in the cycle classification, we have considered a permutation, the cycle structure of permutation. We have compared every index I with sigma inverse of I and sigma of I. Now, when you have a permutation, you can also write it as a word. So consider this as sigma 1, sigma 2, and so on till sigma n. So we say that an index I is a record if for every j less than I, sigma of j is less than sigma of I. This is also known as a left to right maxima. So think of this as, in some sports tournament, let's say some marathon, a record is basically when somebody performs better than everybody who came before them. So similarly, for every j less than I, sigma of j should be less than sigma of I. and that's also known as a left to right maxima. And I, similarly, you can also define an anti-record if I is bigger than j for, sorry, this is a, uh, for every I bigger than j, sigma of I is less than sigma of j. Yeah. So this is known as a right to left minima. So now uh, you can, so you can take an index I, and every index I is one. So you ask whether it is a record or not, an anti-record or not, and you can have four different types. So you can have, it's a record as well as an anti-record. It's only a record but not an anti-record. So in this situation we call it an exclusive record. And then you can have exclusive anti-records, and you can have neither records or anti-records. And now you can combine the cycle classification where you have 5 types and the record classification where you have 4 types and obtain 10, not 20 types. So 4 times 5 is 20, but then half of these are not possible. And so you have the follow. So for cycle values can either be an exclusive record or non-record anti-record. Cycle peaks can be exclusive anti-records and non-record anti-record. Cycle double rises can be exclusive records and non-record anti-record. Cycle double falls can be exclusive anti-records and non-record anti-record. And for fixed points, so whenever you have an index I, which is both a record as well as an anti-record, you can show that that's a fixed point. So fixed points are also come in 2 different types. So you have record anti-records and non-record anti-records. And now you can consider the 10 variable polynomial. So take the sum over every permutation and give this weight to every permutation. So x1 counts the number of exclusive anti-records. So what you did previously with the 5 variable polynomial, except now you also look at the record status and the cycle status simultaneously. Put it on the computer. This has a nice J fraction. So this was proved by Sokal and Zheng in fairly recently. And so you can see that the coefficient of t squared is x1 times y1. And then previously, remember, there was a 4x1 y1, but now this has become an, so you really understand what's going on here. So you have an x1 plus u1, y1 plus v1. So this record, taking into account the record status, has split up the squares as well. So, and here you have x1 plus 2u1, y1 plus 2v1. And similarly, over the coefficients of t, so here you have the contribution of record anti-records is only in this term. And then you have x2, y2 plus w over here, and then x2 plus v2, u2, y2 plus v2, this is a typo, plus w, that's the contribution here. So this is really a nice J fraction that you can obtain in 10 different variables. And so Sokal and Zheng, they then generalize this to 18 variables. They introduce some crossings, nestings, and some queue-like variables, and then their most general version is 5 families of infinitely many variables. And surprisingly, at around the same time, Natasha Blithwick and Einar Steingrimsson found the same results. So they came up on the archive at around the same time. Both of them were looking at these things for entirely different reasons. So Natasha and Einar, they were interested in moment sequences and permutations. So that is the point of view they came in. And Alan and Jiang Zheng, they were interested in continued fractions, and then they converged to almost the same results, surprisingly. But after much later, they figured out that Arthur Randrianarivoni had actually interpreted almost all of these variables for slightly different statistics in 1998. So quite some time ago. And this paper was not cited and it wasn't known. And there were people who had worked. So before these people, Alan and Jiang Zheng and Natasha and Einar, there were people who had done some progress in this line of work in the previous 20 works, but 20 years, but they did not know about Randriana-Rivoni's results. So this is roughly the permutation story. Now, of course, I mean, here, I have counted cycle status, record status, but I have not counted one permutation statistic, which, is really there. I mean, this is one of the first statistics you think about, is the number of cycles. So convert your 10 variable polynomial to an 11 variable polynomial by adjoining the number of cycles. So lambda counts the number of cycles in a permutation. And if you try to put it on your computer, experiment, and then you'll see that this does not have a nice J fraction. But then Allen and Jiang, they found that you can obtain a J fraction by specializing Y1 equal to V1. That is, if you forget the record status of cycle valleys, or you can do cycle peaks as well. But if you forget whether for every cycle valley, whether it's a record or not, exclusive record or not, then you can obtain a nice J fraction. And so this is how the continued fraction looks like. So it's sort of similar, except now you previously had Y1, and then here you had Y1 plus V1, Y1 plus V2, but now you have lambda, lambda plus 1, lambda plus 2, and so on. So you have a contribution of lambda. Sorry, there's also a contribution of lambda to fixed points here, to Z, Ws, and so on, which I forgot to. Okay, few typos. So this continued fraction was conjectured by Allen and Jiang in their paper. They were able to prove it not with one specialization, but with two specializations. They also needed to identify cycle double rises as well. So they had to forget the record status of both cycle valleys and cycle double rises. But then in a recent work, which came out a few weeks ago, so I have managed to prove this continued fraction with just one specialization. So we can count cycles as well. And there are versions of continued fractions counting cycles. So this is roughly the permutation story. And now that I have given you a glimpse of the permutation story, for me to tell you the depermutation story, it'll be fairly quick. So at this point, maybe I'll stop for a while and see if there are any questions.
So are you going to give any hints about your proof or no?
Maybe if I have some time at the end. Yeah, the proof might be, I mean, so Allen and Jiang's paper, that's like a 122-page paper, and although, I mean, they treat not just permutations, they also talk about perfect matchings, they talk about set partitions. So I might give some reference, I'll give some references, but I certainly won't go into the description of the proof, because that would be talking about a lot more things. So yeah.
Okay, carry on then.
All right. So let me proceed. So now that I've told you about, this is the linear picture. Now let me tell you what happens in the quadratic case. So let me go back to depermutations. So recall that depermutations are permutations on 2n letters, and then you have some inequalities, inequality constraints for indexes and values, and these are different for even and odd, whether your index is even or whether your index is odd. Now, what you can do is, we have just defined the cycle classification for permutations, right? We have a 10-variable polynomial, and you can say that, okay, why don't I just simply play the same game? Compute this 10-variable polynomial, x1, x2, y1, y2, z, u1, u2, v1, v2, and w. Play the same game and put it on the computer, ask if this has a nice continued fraction. So in this situation, the continued fraction that we have is not of Jacobi type or Stieltjes type. We have a nice Thron type continued fraction. So it's a Thron type continued fraction is slightly more general than this, but our continued fraction has the following form. So you have these, it's not t squared over here, it's just t's. So alpha 1t, alpha 2t, alpha 3t, and so on. And then there's a delta naught t. And so if delta naught is equal to 0, this is simply a still just type continued fraction. And so if you put these so put this on the computer, you'll find a Thron type continued fraction that has the following coefficient. Oh, this should be a delta 0. That's a typo again. And my coefficients are also okay, several typos. Apologies. So this has been copied from a previous version, and at that time we were So this should be an x1 u1. So this is similar to permutations. So you have x1 u1 y1 v1 x2 u2 w y2 v2 there is w. And so there's a mistake over here in my slides. So now, can we do better? And we can actually do slightly better, because so we did not take into consideration the parity of fixed points. If we do that and separate fixed points by parity, so that is to say, in this 10 variable polynomial, make it into a 12 variable polynomial, except you have two different variables for even and odd fixed points, two more variables. So you have ZE for record, anti-record, even fixed points, and ZO for record, anti-record, odd fixed points, and WE and WO. If you do that, this Z squared becomes a ZE times ZO. So you know that how the contribution of even and odd fixed points are coming. And similarly here, these W's, one of them becomes an even, comes from even fixed points, the other comes from odd fixed points. So that is our result. Yes, this looks better. So you have x1 u1 y1 v1. So x1 and u1 are counting cycle valleys, y1 and v1 are counting cycle peaks, cycle valleys, x2 u2 and y2 v2 are counting cycle double rises and double falls. The y's and z's are counting cycle fixed points. So we have a parity refined classification of, and I mean, when we got this result, it was quite surprising. So I have given this, I have spoken about depermutations quite a bit, and this was before our paper was out. And at that time, we were trying out very different things. But in hindsight, this really looks the simplest thing we could have done, which is consider the same 10 variable polynomial and try and see if this has a nice continued fraction. But at that time, we weren't aware what might be a nice continued fraction. So this was, I mean, quite surprising when the statistics came out to be quite similar to the story of permutations. So in our work, so if you turn off, so depermutations are counting, so these are all different families of permutations, which on 2n letters. So depermutations is the most general thing. If you turn off even fixed points, you get DE semi-derangements. If you turn off odd fixed points, you get DO semi-derangements. And if you turn off fixed points of both parities, you get D derangements. And from our continued fractions, we have recovered these facts, that depermutations are counted by median Genoki, DE semi-derangement and DO semi-derangement are both counted by Genoki, and D derangements are counted by median Genoki again. So this is a very nice sort of families of permutations sitting inside each other. And classically, people had studied D derangements and DE semi-derangements as well as DO semi-derangements. Depermutations are fairly recent. And we, similar to the permutation story, we can also count cycles. So again, this is in two different papers. And if we count cycles and look at the number of depermutations with one single cycle, then we call these D cycles, and these are again counted by Genoki numbers. So you have depermutations, you turn off fixed points of one parity, you get to Genoki. So from median Genoki, you get to Genoki. You turn off fixed points of both parity, you get back to median Genoki. And now you look at only one single cycle, you get to Genoa-Key. So this is the sort of structure that we have realized, and Alex Lazar and Michel Vox have also seen similar structures, but they were looking at hyperplane arrangements. So a different setting. We are looking at continued fractions, and we have recovered this. So once I have told you about the permutation story, talking about depermutations was fairly straightforward. Now let me talk about cycle alternating permutations. I haven't told you what these are. So cycle alternating permutations are a combinatorial interpretation for secant numbers. So the secant numbers, recall that these are the numbers when you look at the series expansion of the secant function and look at the coefficients. So you look at the series expansion as an exponential generating function and look at the coefficients. And these are counted by cycle alternating permutations. So what are cycle alternating permutations? So these are permutations where every index is either a cycle valley or a cycle peak. And so recall that a cycle valley is one where you have I is lesser than both sigma inverse of I as well as sigma of I. And for a cycle peak, I is bigger than both sigma inverse of I and sigma of I. So classically, when people look at combinatorial interpretations for tangent numbers and secant numbers, they do not look at cycle alternating permutations, but alternating permutations, where you consider every letter to be, so you consider a permutation as a word, and every letter is either a valley or a peak. Whereas for our purposes, we find this interpretation more convenient. And similarly, permutation statistics so the linear statistics have been studied quite extensively. So you can also classify, just like the cycle classification, where you have cycle valleys, cycle peaks, cycle double rise, cycle double fall, and fixed point. You also have linear classification, peaks, valleys, fixed points, and double rises. So now, so the secant numbers are simply every index is either a cycle valley or a cycle peak. And again, recall that this was the 10 variable polynomial for permutations, which we saw a few slides ago. I have copied it here again. And so to obtain a continued fraction for cycle alternating permutations, you simply put x2 equal to y2 equal to u2. So turn off all the variables counting cycle double rises, cycle double falls, and fixed points to 0. If you do that, so now you will be working with 4 variable polynomials. So these look at just cycle peaks, cycle valleys, and then look at the record status. And take a sum over all cycle alternating permutations. Then this has a nice S fraction. So this looks like 1, and then here you have, so recall that secant numbers, just the numbers, had alphas 1 squared, 2 squared, 3 squared, 4 squared, and so on. Now you can see that these numbers, now you can obtain more stratified information. In every square term, so the alphas are n squared, and so you should think of it as n times n, and one part of the contribution is coming from cycle peaks, the other part is coming from cycle valleys. So you have x times y, x plus u times y plus v, x plus 2u times y plus 2v, and so on. So in fact, we can even do better than this. We can separate the cycle valleys and cycle peaks by parity and consider not a 4 variable polynomial, but an 8 variable polynomial. So look at even cycle peaks and odd cycle peaks, similarly even cycle valleys and odd cycle valleys, and then separate by records status. And if you put it on the computer, you will see that this has a simple S fraction. So this is XCYO. So this is even cycle peak. This contribution is coming from odd cycle valley. Here you have odd cycle peak, even cycle valley, again even. So you have even, odd, odd, and then odd, even. And so here you see that so you understand that the alphas even heights and odd heights have contributions coming which are, depend on the parity of the indices. So this was actually a small observation of a more general result of Sokal and Zheng involving, so their most general result for cycle alternating permutations involves two infinite families of variables, but they had not noticed when they were working on this paper. And then, so this came out on the archive a few weeks ago. So we noticed that you can actually say something about the parity of the cycle peaks and cycle valleys. And you can also count cycles here, similar to depermutations and permutations. So instead of having an 8-variable polynomial, put a 9-variable polynomial. And now again, you need to identify, you need to forget the record status of cycle values. And you obtain a similar continued fraction. So you have a lambda term. And so earlier you had YO plus UO, 2UO here, but now, so that has disappeared. And you get the contribution of, you can count cycle alternating permutations with number of cycles. And if you do this and just look at the coefficient of lambda, so that is, you consider cycle alternating permutations with one single cycle. We call these alternating cycles. So these are permutations that have a single cycle, and every index is either a cycle value or a cycle peak. Then these alternating cycles are counted by tangent numbers. So this is very similar to the depermutation story, where you have d permutations and then d cycles, and so you have you keep switching between median Genoki and Genoki. Here you keep switching between, so well, it's happened only once. You have switched from secant numbers to tangent numbers, and maybe I should mention as a problem. So the E2n's 2n plus 1. So look at, so these are tangent numbers E2n minus 1, but then look at the next tangent number E2n plus 1. They are still less than 2n factorial. So there must be some family of permutations whose cardinality is tangent numbers, which contains cycle alternating permutations. We do not have a nice description. We do not know what they can be. So if somebody knows or can find out, please let us know. So I'll very quickly tell you about Jacobian elliptic functions, about which I've only learned recently. So, and I'm sure people in this audience are, know a lot better than me and probably can correct some historical inaccuracies if I have any. So you can define U to be this function, this integral, and then the Jacobian amplitude is the inverse of this function f. So you invert f, and so amplitude. So it's a function in two variables. And the Jacobian elliptic functions, so these are doubly periodic functions. And so Sn of u comma k is sine of this amplitude, and Cn is the cosine of this amplitude. There are more Jacobian elliptic functions, but actually, I mean, in hindsight, I didn't even, okay, let me go ahead. So this is how the Jacobian elliptic functions are defined. And there are combinatorial interpretations due to Dumont, and also several other people, I should have mentioned them. So there's Vienno and also Flageolet and Franson and other people have also found combinatorial interpretations. But we have been following the work of Dumont. He introduced something called Shet polynomials. I thought I might have some time to go into Shet polynomials towards the end of this talk, but I don't think I will. So I will not. And so I did not prepare the slides. I was quite ambitious while making the abstract, but have not done that. So again, similar to the secant numbers and tangent numbers, take the Jacobian elliptic functions and look at their series expansion around u. So with the variable u, and so for Sn, the contribution only comes at the odd terms, odd order terms, odd coefficients, and for Cn, the contribution is only the even coefficients are non-zero. And these E sub 2n plus 1 of k and E 2n of k, these are polynomials in k. And so I will only give you a continued fraction for the E2n's, that is for the cos amplitude Jacobian elliptic function. So if you look at these polynomials, which are the coefficients, so Stiljus had discovered this in 1889, that they have this S fraction. So you have 1 squared, 2 squared, k squared, 3 squared, 4 squared, k squared. So this is a generalization of the continued fraction for secant numbers. So in fact, if you put k equals 1, I think you should get secant numbers here. So that's 1 squared, 2 squared, 3 squared, 4 squared, and so on. So this generalizes the continued fraction for secant numbers. And Stiljus had discovered this in 1889. So maybe somebody in the audience can tell me if Ramanujan had rediscovered this continued fraction as well. I mean, maybe I should look into Ramanujan's notebooks and try and search for this. Also, this was proved by Rogers using something called Rogers addition formula. So our continued fractions also generalizes this, because we look at the even and odd levels separately. So let me just go back a few slides. So you see, you have even terms which behave differently from odd terms. So these things count cycle alternating permutations, where you put different weights for even and odd indices. So parity refined indices. And so our continued fraction understands this combinatorially. And before going into towards the end of my talk, are there any questions? Maybe I'll wait for a few seconds, 5 to 10 seconds. Okay, so let me proceed. So finally, I will give you a glimpse of something called the Jacobi-Rogers matrix. So consider the Jacobi type continued fraction. So this is the most general form of the Jacobi type continued fraction. So you have betas, which are coefficients of t squared, and then you have gammas, which are coefficient of t. So again, recall that if you're maybe some of you might be calling them associated C fractions. So outside of combinatorial literature, it's called associated C fractions. And now, from this J fraction, you can define a certain lower triangular matrix, J. So the coefficients are, so it's a unit lower triangular matrix. So the coefficients on the diagonal are simply 1. And J and K is given by this recurrence. So you have a 4-term recurrence. So J and K is Jn minus 1, K minus 1, plus gamma K times Jn minus 1, K, plus beta K plus 1 times Jn minus 1, K plus 1. So those of you in the audience who know about Flageolet's combinatorial interpretation of continued fractions, the Nk entry, this counts the number of Motzkin paths from the origin to n comma k. So this has also been known as the Stiljus table or the Stiljus tableau. And Stiljus had knew about these things and had worked with some of these. I think I have not looked at this carefully. I should probably read more about the history. And so one thing which I want to mention is, if you begin with a sequence an, oops, this should be t power n, not t sub n. That's another typo. If you begin with a sequence, a series, this is the ordinary generating function of the sequence an, and write it as a J fraction, then you can see that the 0th column of this matrix. So we are indexing our matrix. It's a doubly infinite matrix. We are indexing our matrix from 0, not from 1. And so you look at the 0th column. So look at the entries Jn comma 0. These are simply the numbers an. So this is a question one can ask. that if you have a Jacobi type continued fraction for a sequence an, then maybe try to combinatorially understand not just the 0th column, but the entire matrix. And let me tell you a special case. So when an is n factorial, again, the same typo here. This is what happens when you copy things from one slide to another. So you have this J fraction, which we saw. So you had the odd numbers as gammas and squares as betas. And one can see that from the recurrence, you can prove this, that J n k is equal to n choose k times n factorial over k factorial. So this has a nice closed form formula. And these things count, these are the number of Laguerre digraphs with k paths. So I haven't described what Laguerre digraphs are. I'll do this in the next slide. So what's a Laguerre digraph? So Laguerre digraph, it's a labeled graph. So it's a directed graph. Every vertex has a label. And every vertex has in degree 0 or 1 and out degree 0 or 1. Let me give an example. So this is a directed graph on 11 vertices. So you can see that every vertex has, so for example, 1 has an in degree of 1 and an out degree of 1. 5 has an in degree of 1 and an out degree of 1. However, 9 has an in degree 0. So it has no predecessor. Similarly, 10 has an out degree 0. 11 has in and out degree both 0. So we call these Laguerre digraphs. And each connected component in a Laguerre digraph is either a cycle, oops, this isn't a peak, or a path. Sorry, that's a typo. So this is a cycle, this is another cycle, and then you have a path with 2 vertices, a path with 3 vertices, and a path with 1 vertex. And if you have no paths, then that is simply a permutation. So that's a permutation, and you look at the cycle structure of permutation, and you can draw it as a Laguerre digraph with no paths. And so by the way, so in some people also call these things as partial permutations. Some people also call these things as Laguerre configurations. So I think they were first used by an analogous concept was used by Fuata and Strel. And they used it to describe coefficients of Laguerre polynomials. And they called it Laguerre configurations. We use the term Laguerre digraph because we think of these as digraphs, directed graphs. And if you count the number of Laguerre digraphs where you have n vertices and k paths, another typo here. So you have n vertices and k paths. That is counting the entries of the Stieltjes-Rogers, Jacobi-Rogers matrix of if you start with the sequence n factorial. And this is still ongoing work. We can extend our permutation statistics from Laguerre digraphs, from permutations to Laguerre digraphs. So again, let me repeat, Laguerre digraphs are a generalization of permutations, and we can extend permutation statistics from permutations to Laguerre digraphs. So previously, we had a cycle classification. Every index could be classified as a cycle peak, a cycle double valley, a cycle double rise, cycle double fall, or a fixed point. For a Laguerre digraph, every index can be classified either as a peak, not a cycle peak, a peak, valley, double ascent, double descent, or a loop. Or also another, you can also have isolated vertices. So let me just tell you. So for example, 5 is a loop. Loop in the sense of graph theory, in the same definition of loops that you have in graph theory. So 5 is a loop. So 1 is less than both its predecessor and successor. So 1 is a valley. 7 is a peak because 7 is bigger than both 4 and 3. Now we can have some boundary conditions. So let's say if we have 0, 0 boundary condition, that is, if 8 does not have a predecessor, so any vertex does not have a predecessor or a successor, we can pretend it has a predecessor or successor of 0. Then we can also define valleys and peaks and double rises, double falls, and so on. Or we can have you can fix your boundary conditions. You can have 0, 0, 0, infinity, infinity, 0, or infinity, infinity, and then accordingly your definition will slightly change. And we can extend our interpretation of the Jacobi-Rogers matrix to count cycle classification. We can also do record classification. So this is still ongoing work. However, the work on, so now I'll tell you about a subclass of Laguerre digraphs, which we call alternating Laguerre digraphs. So these are digraphs where every vertex is either a peak or a valley. So as you can guess, these interpret the Jacobi-Rogers matrix for the secant numbers. So, so let me just again go back to this picture of Laguerre digraphs. And here, for example, 11 would be considered is not a peak or a valley. So we do not allow something like this. Or for another example would be 3 is neither a peak nor a valley. 3 is a double rise. So we do not allow something like that. So an alternating Laguerre digraph is a Laguerre digraph where the vertices are alternating. And if you have no paths, that's simply cycle alternating permutations. And if you allow paths, this interprets the Jacobi-Rogers matrix for secant numbers. And finally, so I'm in good time. So finally, I'll end with a question. So we have a combinatorial interpretation. So this is the S fraction for permutations, 1, 1, 2, 2, 3, 3, and so on. And we can also put in statistics and understand this, putting in a lot of information, get a lot of information out of this. Now the question is, understand when you have 1 squared, 1 squared, 2 squared, 2 squared, that is median Genoki. We have seen that a while ago. But what about 1 cubed, 1 cubed, 2 cubed, 2 cubed, and so on? So k equals 1, that's the quasi-linear case. K equals 2, that's the quadratic case. But for cubic and above, not much is known. So there is one work of, there's a work of Flageolet and Eric Conrad, and they describe continued fractions for Dixonian elliptic functions, and the coefficients grow cubically. So that is like one of the few things which is known about the cubic case, but otherwise not much is known about cubic. I don't know if anything is known about quartic at all. Cubic case was rediscovered by, it's there in Ramanujan's notebooks. And this I know that the cubic case Ramanujan had this. So here are some, I'll end, and here are some references. I'll just keep at the slide, and thank you.
Thanks a lot, Vishal, for this lovely talk. May I invite the audience to ask questions or give comments, suggestions?
So maybe I can say something about the proofs. Gaurav, you wanted to ask that? Did you have something else you wanted to ask?
No, I mean, just what's the basic idea of the proof? Do you get some recurrence relations, or I mean, just whatever?
It's the proofs are bijective.
I see.
Entirely bijective. So we take Flageolet's interpretation of continued fractions. So once we have experimentally found continued fractions, we know that they should be in bijection with some sort of paths. So if you have a J fraction that's Motzkin paths, if you have an S fraction that's Dick paths, and if you have Thron type continued fractions, that's Schroeder paths. And then we construct bijections onto those paths. And there are some classical bijections, and our work is built up on those bijections, in particular 2 bijections. So there is the Foata-Zeilberger bijection, and I have This is one of my recent archive preprints. So there's the Fuat-Zeilberger bijection, and there is something called the Bian bijection. And usually when you want to do cycle counting, people mostly use the Bian bijection because you have Laguerre diagrams coming up and then you can see how the cycles are built. Whereas if you want to do cycle counting, so it was believed that maybe you cannot use Fuat-Zeilberger bijection. It wasn't obvious. And that is a recent work I've done where I show that you can actually count cycles using the Fuat-Zeilberger bijection. So there are these two bijections, which are, so our work is sort of derived, I would say, from by really understanding these two bijections in some depth.
Okay, so one further comment or query, can you go back to your generating function, just any one of those results?
Yeah,
where the multivariable thing comes.
This, for example.
Yeah. So I mean, in Q series, we normally do Q raised to the power some statistic. So this would be not considered 9 variable, but 9 basic. So these x's and y's, x0, y, xe, xo are considered as bases.
Right.
If you're looking at Q analogs, I mean, if you're thinking of them as Q analogs. So yeah, I mean, maybe one of these guys can be considered as a parameter, but yeah, I mean, we would call them multi-basic rather than multivariate somehow.
So we have Q-like variables. So you can replace these numbers 1, 2, not in this version, but yeah. So you can replace the numbers 1, 2, 3, and so on. We have interpretations where you replace them with PQ numbers. So homogenized Q numbers, and we can interpret those as well. And so I have not mentioned it in this talk. So you need some more statistics, and this can be generalized. So we have, Alan likes to call them X-like variables and Q-like variables.
I see. So you're saying they're different, actually. They're
yeah.
Not
yeah. So I haven't gone there in this talk, but we can do that.
Okay. All right. Thank you. Yeah.
Okay.
Actually,
yeah,
I have a
ahead,
question.
Michael.
Yeah. Thank you, Bishal, for the interesting talk. Nice results. So my question is concerning, do you know the property enjoined by Eulerian polynomial as well as other polynomials that the coefficient sequence being gamma positive? So if I recall it correctly, continued fraction could also be used to show the gamma positivity. So essentially, your work, in some sense, refined this, or getting deeper for this continued fraction. So does it help to refine maybe the gamma expansion?
Yes. The answer is yes. And I mean, I have not. So we have not worked on gamma positivity. But so what if you're working with continued fractions, what one can do is, if you begin with let's say you have a sequence, assume that it is gamma positive, write out the coefficients and expand its j fraction. It's actually, it's like if you have j fractions which have a certain form, you get gamma positivity out of that. So there is, we have not explored that aspect of it, but so there is the paper of this paper of Jiang Zheng and should be Sokal and Zheng, sorry, that's the order should be switched. So Jiang Zheng and Sokal, so derived from this paper, there have been several results by Jiang Zheng and his students, Bin Han and also Cheong Pan, and they have proved several gamma positivity results for Eulerian polynomials, I think type B Eulerian, and various classes of polynomials by as corollaries of the continued fractions here. So that can be done, yes.
Yes, thank you. but maybe not for the the Jacobi elliptic case, the shed polynomial. You just briefly
Yeah,
mentioned in the end.
so I mean, we are currently working on shed polynomials, and I mean, I do not know about gamma positivity there. I did see that there were some, I think, fairly recent papers on the archive, maybe 2 years ago, while yeah, by uh, Ma and Mansoor and
Yes,
a few other authors.
Zhichong was a previous student of Jiang Zhen. Lin,
Yeah,
last name Lin. L-I-N.
yes, possibly. So I did notice I have not studied gamma positivity there. So one thing is, I mean, so you have special cases of the shed polynomials if you're yeah, so where you have classical continued fractions, but in general they do not have nice continued fractions, and so gamma positivity results are there, I would guess, is slightly different. I have not studied that in yeah, in detail. So we have not explored gamma positivity. So we are mostly interested in continued fractions, but maybe I don't know.
I
So
see.
we are
Yeah.
maybe a year from now or in 2 years, I might be able to say something about shed polynomials as well and continued fractions.
Hopefully. Yeah.
Yeah.
Nice talk.
Thank you.
Yeah, and if any comment I could make is that in Ramanjan's notebook, there's some, I would have to check that very carefully, but yeah, the cubic rise was for version of the Hurwitz zeta function evaluated theta 3 comma x, and quadratic rise was for zeta 2 comma x. Strange functions come up. I'm not very sure how you would interpret them combinatorially.
Okay, I see. I see.
There
This
are
is
some,
interesting. Yeah, I did not know about this. Okay, maybe I should email you and ask.
I'll
Yeah,
share
ask you for the references.
Yeah, references, definitely.
Yeah.
So if there are more comments, we wait for them. We thank the speaker again. Thank you.